Okay, hello there. Welcome back. What I want to do today is to look at AC motors. Now, again, you're not going to be able to see what I'm saying at this point in time, but you'll need to look at the video called AC motors. Okay, AC motors. Okay. Now, a lot of this you're going to have to read through yourself, and you're going to have to make notes. You're going to have to put pen to paper. You will have to extract information that is relevant to you. Also, you will need to look at your own style of learning and how you want to modify the work or adjust it to accommodate yourself overall. Okay, but nonetheless, we're going to look at this now. Bear with me. Okay, while I interesting. Okay. Okay. Yeah, I'm here. Good. Sorry about that. It always happens at the wrong time. Mamma mia. Close. Oh, uh, didn't I set you to? Didn't I set you to? Okay. 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 It's okay. You can never get this to work the way you want it to work at the time you want it to work. Okay. Now I have quite a bit of work here to go through, but what I want to do is to make sure that it's understood by everybody. So let me just pan back a bit and make sure that I can get the work into view. Okay. And let me just change the angle of this slightly. Okay. Now polyphase. Now we're looking at AC motors, and we're going to start off with polyphase AC motors. Now, polyphase squirrel cage AC motors are basically constant speed machines, but some degree of flexibility in operating characteristics results from modifying the rotor slot design. These variations in AC motors produce changes in torque. So when you have an AC motor, what you're looking to make sure that the motor can lift and rotate the load that you have in mind. And the motor can do that when it can develop a good torque. Okay, simply means pulling power. Changes in torque, current, and full load speed. Evolution and standardization have resulted in four fundamental types of AC motors. Let me just close this door here so I don't get any noise. Sorry about that. AC motors, designs A and B. Now, when you say designs A and B, it's simply the status when you're designing the motor. It could be a class A, class B, class C, class D, etc. So what you're looking at is whether it's an A or B, and what we're looking here at the moment is A and B. General purpose is AC motors with normal starting torques and currents and low slip. Fractional horsepower polyphase AC motors are generally design B because of the drooping characteristics of design B. Sorry. When it says drooping characteristics, what it is showing, you'll see a bit later on, is the characteristics of design B, how it has a droop in it, basically. A polyphase AC motor that produces the same breakdown maximum torque as a single-phase AC motor cannot attain the same speed torque point for full load speed of single-phase AC motors. Therefore, breakdown torque must be higher, a minimum of 140% of the breakdown torque of single-phase general purpose AC motors, so that full load speeds are comparable. AC motors design C, high starting torque with normal starting current and low slip. AC motors are normally used where breakaway loads are high at starting, but which normally run at rated full load and are not subject to high overload demands after running speed has been reached. In short term, you don't want the motor to overrun itself to death, otherwise it will simply burn out. And you don't want that. You want the motor to be able to continue to work at a efficient speed without running away. Okay. AC motor design D. High slip AC motor, starting torque, low starting current, and low full load speed. Because of the high slip, speed can drop when fluctuating loads are encountered. This AC motor design is subdivided into several groups that vary according to slip or the shapes of the speed torque curve. Now I'm keeping my camera back a bit because I don't want to get too close in. Sometimes it doesn't allow me to, it overshoots. When I think it's in frame, it's not. Okay. AC motors design F. Low starting torque, low starting current, and low slip. So if you have a motor with design F, you can be sure that it will have a low starting torque, low starting current, and a low slip. Now you need slip to ensure that the motor runs. If there is no slip, there is no rotation. These AC motors are built to obtain low locked rotor current. Both locked rotor and breakdown torque are low. Normally, these AC motors are used where starting torque is low and where high overloads are not imposed after running speed is reached. So what you're saying here is that you don't want the motor will continue to run at its agreed speed, providing you do not put an excessive overload on it. Okay, and that's what you have to bear in mind, that motors are designed to carry a given load. If you're carrying more than that load, you will have problems. Okay. AC motor basics of AC motor design engineering. Now AC motors heading. Now when you go to the AC motors video, you have all of this on here. So you'll be able to see what I'm talking about at this point in time, hopefully. Wound rotor AC motors. Squirrel cage AC motors are relatively inflexible with regards to speed and torque characteristics, but a special wound rotor AC motor has controllable speed and torque. Application of wound rotor AC motors is markedly different from squirrel cage AC motors because of the accessibility of the rotor circuit. AC motor performance characteristics are obtained by inserting different values of resistance in the rotor circuit. So what you can call an outboard panel with variable resistors in it. So by changing the resistors load, you can control the speed or the torque of the motor. Okay. Wound rotor AC motors are generally started with secondary resistance in the rotor circuit. The AC motor resistance is sequentially reduced to permit the motor to come up to speed. Okay, star delta. You can refer this to a star delta starter. So you push your handle up. Okay, you push up the handle, and then the motor slowly begins to wind around and start up. And as it begins to reach maximum load, you put it to run. Okay, and the motor then takes over and runs at its full correct speed. Because AC motors can develop substantial torque while limiting locked rotor current. This secondary AC motor resistance can be designed for continuous service to dissipate heat produced by continuous operation at reduced speed, frequent acceleration, or acceleration with a large inertial load. External resistance gives AC motors a characteristic that results in a large drop in revs per minute for a fairly small change in load. Reduced AC motor speed is provided down to about 50% with speed, but efficiency is low. Okay. Multi-speed AC motors. Consequently, pole AC motors are designed for one speed. By physically reconnecting the leads, a 2-to-1 speed ratio can be obtained. Typical synchronous speeds for 60 Hz AC motors are 3,600 to 1,800 revs per minute. Now that should probably be the other way around, okay? 1,800 to 3,600. I have no idea why I did that like that, but probably for a reason, okay? And that's 2 to 4 pole, 1,800 to 900 revs per minute, 4 to 8 pole, and 1,200 to 600 revs per minute, 6 to 12 poles, okay? Now remember, you up with poles of motors, you're working in pairs per poles. So if you have 6 poles, obviously you're going to have 3 pairs. Okay, if I remember correctly. 2-winding AC motors have 2 separate windings that can be wound for any number of poles so that other speed ratios can be obtained. However, ratios greater than 4-to-1 are impractical because of AC motor size and weight. Single-phase multi-speed AC motors are usually variable torque design, but constant torque and constant horsepower AC motors are available. Okay. The power output of multi-speed AC motors can be proportionate proportioned to each different speed. These AC motors are designed with output horsepower capacity in accordance with one of the following load characteristics. And here I'm showing you AC motors, variable torque AC motors have a speed torque. For example, 1,800 revs to 900 revs per minute. Okay. Since AC motors face loads such as centrifugal pumps, fans, and blowers have a torque requirement that varies as the square or cube of the speed, this AC motor characteristic is usually adequate. And again, AC motors, constant horsepower. Okay. Now here again we have AC motors come in multi-speed type, but there is a practical limit to the number of speeds obtained. Okay, all I'm doing is just taking extraction from this for you from myself. Okay, but this is for you to mainly look at and read for yourself. AC linear electric motors. The first linear electric motor was conceived by Wheatstone more than 100 years ago. But large air gaps and low efficiencies prevented linear electric motors from being widely used. Although electric motors still have relatively large air gaps, linear induction electric motors are increasingly chosen for material handling applications because they are quieter, more reliable, and less expensive than rotary electric motors. And because linear electric motors do not drive gearboxes or rotary to linear conversion devices, they can be more efficient. Again, for you to observe and to read for yourself. I'm hoping that I can get this on. Okay. Again, this is for you to look at and to read for yourselves. Hopefully, it's providing you with information that you can use or extract to make up your own. And here we have something called definite and special purpose motors. Definite purpose motors handle. Sorry, I'm going to put my teeth in. Definite purpose motors handle specific applications and have well-established NEMA standards. They are produced in high volume and are low in cost when compared to general purpose motors with the same ratings. Okay. Again, I'm not going to spend a lot of time reading through this overall. Mainly it's for you to look at and extract and make your own. Okay. And here we have something called motor starters. Full voltage single speed motor starters. Single speed squirrel cage motors have starters that fall into two categories: full voltage or across the line starters and reduced voltage starters. Full voltage starters, manual and magnetic, apply full voltage directly to motor terminals. Two other types, combination and reversing starters, consist of a starter, usually magnetic, with added functions. Okay. multi-speed motor starters, etc. here, okay? But I don't need to go into that for you. You can read it for yourselves, okay? Let me just go back. I've got the light back on it. Just go back, make sure that I've got that light fully on it. Okay. Okay. Just make sure that I've got it in frame. Okay. Now here, specific winding information, controllers for synchronous motors, etc. You have a lot of information here which you can use for yourselves, okay? Okay. Induction motors we have here as well, okay? And let's look at the NS equals 120 F over P. And here you have where NS equals synchronous speed, F equals the frequency, and P equals number of poles. Now I've not something come to me to my mind, pairs of poles, but maybe I'm thinking of something else. But it'll come to me in due course. Now this one here, let me just see if I can make it bold for you, okay? And a little bit bigger. Okay. Okay. And hopefully you can see that, okay? Let me see if I can highlight it. Bear with me for a second. Just to make sure that it's visible to everyone, basically. You never know how these things are going to come out, okay? So hopefully that will be useful. That's S equals N open bracket NS minus. Well, here you have what it is, where S equals slip, NS equals synchronous speed, and NA equals actual speed, okay? And here you have your waveforms, but the waveform here hasn't come out quite good. So what I would recommend you do is to look up the torque to speed ratio in regards to the waveform for different types of motors, okay? Design D and design B, okay? So that's a little job for you to be doing for yourselves. Let me see if I can, what I can do with this here, if I can make it bolder. Let me just try that and see if it improves it. Okay. Hoping so. Okay, but no guarantee on anything. Okay, it's just the way it comes out at times. And let me see if I can make the U a little bit bigger. No, I'm more concerned about making things bigger so that it's easier to see. Okay, and easier to follow. Okay. Wound rotor motors, and here you have vary according to slip or the shape of the speed torque. Okay, and here you have start windings, okay, running windings, etc. Okay, 4 poles. There's 2 pairs of poles, okay, basically here. Okay. I'll start one now. I've given some windings, start windings on in regard to motors before. So make sure that you look at that yourselves, okay? And so you know what we're looking at, okay? Let me just bring you closer to so you can see him, okay? Let me just pan back a bit, okay? And here we have brushless DC motors, okay? Again, make sure you're familiar with that and the winding, running windings and start windings, okay? Completely different. You have a centrifugal switch. Now here, I'm not going to do anything here purely for you to read and to see what information you can gather and utilize from this, okay? Coreless DC motors, okay? So coreless DC motors. The development of moving coil or coreless motors dates back to the middle 1930s, but it wasn't until the early 1960s that they were produced economically enough to gain wide acceptance. Now, the major advantages of coreless motors include very low inertia, low mechanical time constant and high efficiency. Because the core is ironless, its low mass allows more rapid acceleration and deceleration than any other class of DC motor. Okay. The flux lines extended radially, etc. So that again is for you to look at and read. I've tried to highlight some of this work so that you can make it easier for people to view and to take those other people into account. Okay. So I hope that it has worked for you all. Now here we have AC DC motor dynamo, if you like. Okay, which used to be in my car many moons ago, but we have alternators now, not dynamos anymore. Okay. And here you have different types of motors. And this is an alternator, which you'll find on your vehicle. Okay. And this is just its construction. Okay. And finally, it's just showing you here. Now you're not going to see this too good, so I accept that. But the idea is to show you that how these would have been wired at one point in time. Okay, I hope you found this useful. Okay, and I'll just like to say good night for now. Let me see if I can make my way all the way back up. Taking everything into view, make sure that it's all covered. Yes. Okay. I'm just recapping what I've done, making sure that it's on in frame and on my camera. Okay. But I'm gonna have to run it again and check. Some folds I leave on, but if I'm not happy with it, I will redo it overall. Let's see what we can come up with. Okay, we're getting there, I think. And we are at AC Motors, okay? And thank you for your time. Have a good day. Bye-bye. Okay, again, you'll need to look at AC Motors in regards to the video, okay? And I hope you may find that useful. Bye-bye.